All right, so when we talk about acid-base titration, essentially what we're doing is we're taking a acid or base that we know the concentration of, and we go ahead and we add that to some acid or base that we don't know the concentration of. We monitor the reaction with either a pH meter or an indicator that determines what's called the equivalence point. The equivalence point, of course, being the point where you have neutralized all of the acid or base, or in other words, when you have the same number of moles of acid as you do base. In fancy terms, we would say that the equivalence point is the point at which the acid and the base are stoichiometrically equivalent. Okay. So if we want to actually look very deeply at what's going on during a titration, we can create a titration curve, and this requires us to use a pH meter and graph pH as we add an increasing volume of our known acid or base. Okay, we use it to determine the equivalence point, and it can also help us to determine what would be a suitable indicator for titrating a particular acid. Finally, but last but not least, we can use a titration curve to determine the Ka or the Kb of a weak acid or base. So we'll go through all of how to do those things today. So when we look at a titration curve, we have 5 scenarios. Let's say we have an unknown strong acid, and we titrate it with a known strong base, or the opposite of that, a known strong acid with an unknown strong base. Okay. The other next two situations we have are what happens if we have weak. So an unknown weak acid with a known strong base, a known weak acid, and an unknown strong base. And then last but not least, polyprotic acids being titrated with a known strong base. We can also have weak bases being titrated, and that's just essentially the opposite of the scenarios with the weak acids. All right, so for each of these, the best way to think about it is, as we move through different parts of the titration curve, what's going on at different points along the way. In other words, what species do we have in the beaker? Okay. And how does that contribute to how we might deal with the pH? Okay, so take a look at this, and go through the different scenarios here, the different points along the titration curve, and see if you can kind of understand what's going on when we take a strong acid with a strong base. Okay, so one way to think about this is, since we're talking about strong acids and strong bases, we've got full dissociation, right? So when I first go ahead and put my unknown strong acid, let's say it's hydrochloric acid, into the solution, in the flask, if you will, we have hydrogen ions and chlorine ions. That's all we've got, all right? Then, as I start to add the NaOH, okay, that's our strong base, the OH is going to react with the H plus to make water. So what does that mean? Well, it means that we have less and less H plus, and we have some Na now appearing in the solution that was left over after the OH reacted with the H pluses. Okay, so then eventually we get to a point where all of the OH reacts with all of the H, and at that point we have no OH left in solution and no H left in solution, but we do have the other ions in there. So in this particular case, it would be our sodium ions from the NaOH that was added, and the chlorine ions from the HCl that was added at the very beginning. So there we have it at neutralization. In other words, when all of the H plus is neutralized by the OH. Okay, so then you have this very rapid increase in pH right there that's centered with the equivalence point. And then after that, basically what you're doing is you're just adding more NaOH to the substance, to the solution. So as a result of that, you're just ending up with excess NaOH. So we add more NAs and we add more OHs going on with there. Okay. Now, you'll notice that leads to different pHs here along the curve. Why? Well, at that very initial point, we essentially have our strong acid HCl in there, and we know that if we want to figure out the pH of that, it is just the pH of the strong acid. So we go ahead and we use the concentration then we would figure out what the pH of that is at that point, okay? So then, between there and the equivalence point, the pH rises slowly at first, okay? Why does it rise slowly? Well, we're slowly but surely taking out just a little bit of H plus at a time. And so that's going to cause the pH to go up and up and up and up and up, okay? So the pH then at that point is the pH of the acid not yet neutralized. So at this point, it's essentially just a stoichiometry problem followed by a pH calculation, okay? Then at the equilibrium point, equivalence point, that's where we have neutralization. And for a substance where we have strong acid and strong base, that neutralization is, pH is 7.0, because all we essentially have in there is water, and then we have the ions of some salt. In this case, it's NaCl. Okay, and we know that Na is the conjugate of NaOH, and Cl is the conjugate of HCl. Those are both strong acids and bases, so there's going to be no effect on the pH there. So it's got to be neutralization at 7, because all we have is water. Okay. After the equivalence point, the pH rises rapidly and then slowly. Well, what's going on there? Well, all of a sudden you are adding a whole bunch of extra hydroxide ions. And so at that point, in order to figure out the pH, you would simply go 14 minus the pOH of the excess strong base. So again, at that point, it's a stoichiometry pOH to pH problem. Okay. If you have an unknown strong base with a strong acid, you essentially have the exact same concept as what we just talked about, but we have a reverse curve. Okay, so here's our strong acid with a strong base. Here's our strong base with a strong acid. And so again, we would start off with just the concentration of the OH. Slowly that OH concentration goes less and less and less, so the pH comes down. As we get to the equivalence point, there it is, 7 again, because in this case it's strong acid, strong bases, so their salts are going to be the conjugates of strongs. And then after that, we have excess acid, and so again, our pH at that point would become the concentration of the excess acid. All right, so things get a little bit trickier and more interesting when we start talking about titrating a weak acid with a strong base. Okay, so once again, we're adding NaOH. This time we're going to use acetic acid in solution before titration. So basically, in the beginning, you have your acetic acid in an equilibrium situation with H plus acetate. Okay, so then, as we start to add NaOH to this solution, the NaOH is going to react with the H plus to make water. Okay, as it does that, it will shift the equilibrium, putting more and more HAC into solution. Okay, so that means that you end up with a bunch of water molecules new water molecules being made. Your amount of HAC is going down. There's no H plus in there because it's being consumed by the NaOH. Your amount of AC minus is starting to increase because of being pulled off, the hydrogens being pulled off the acetic acids. And last but not least, you also have Na pluses in solution left over from the hydroxides that are leaving them. Okay, so as this process goes on, these two things are rising. Those two substances are rising, and the HAC is going down. Okay, so then once you get to neutralization, the HAC is completely gone at this point. So you end up with, again, all the waters that have been made. You end up with AC minus ions, and you end up with Na plus ions. Okay, then last but not least, you start adding more sodium hydroxide after that. There's no acid left to react with the excess NaOH, so you end up with H2O, AC minus, Na plus going up, and OH minus going up. All right, so if we're going to start looking at pH with this situation, we've got some new considerations. Okay, our initial pH is based on an equilibrium situation, so Ka is going to become important. In a little bit later on, you'll see that we end up with a buffer situation where we end up with the weak acid as well as its conjugate base. And we'll also see a situation where we end up with needing to deal with the pH of a salt. Okay, all of those things come into play as we move along our curve. How so? All right, well, way back here in part 1, we're talking about the initial conditions. So again, our species are HA, H plus, A minus, and water. So our pH is going to be determined using Ka to find the concentration of H. Between the initial pH and the equivalence point, so anywhere in this region of 2, essentially what's happening again is the weak acid gets neutralized by the base, conjugate base is being formed. So you end up with the weak acid, its conjugate base, the water, and a cation from the strong base. Okay, because I've got a weak acid and its conjugate base, that creates a buffer system. And so essentially the pH here is going to be determined by buffer procedures. You're going to do the stoichiometric calculation first, and then use Henderson-Hesselbalch. So the idea here, again, is here's our stoichiometric calculation using our weak acid, strong base reaction. Then once we've got that taken care of and figure out where along the curve we have, we're going to have new values for the concentration of the weak acid and the conjugate base here. And we'll go ahead and use those along with Ka and the Henderson-Hesselbalch equation to figure out the pH. All right. So that continues until we get to step 3. And at step 3, we are at neutralization. So at the neutralization point, all of the weak acid has been consumed, and all of the strong base, the hydroxide, has been consumed. So what we have left is water, the cation from the strong base, so in this particular case, that's the sodium, and we have our conjugate base of our weak acid, A minus. All right, so this, in effect, then tells us that we've got a salt solution pH problem coming up here. The moles of our weak acid that we started out with are going to be the moles of the conjugate base that are sitting in here, in this case, the acetate ion. Okay, so the strong base cation does not affect the pH. The Na is not, because it's the conjugate of that is the NaOH, which is strong, so that doesn't affect the pH. However, the conjugate base of our weak acid does cause the solution to become more basic. Why? Well, because, again, having the conjugate base of a weak acid sitting in water creates an equilibrium situation where it reacts with the H plus ions to make HA, and that produces OH minus. Okay? So again, you end up with a situation then at that point where you are dealing with salt procedures. Okay? After the equivalence point, what you have then at that point is the pH rises rapidly and then slowly. And at that point, all that's really important at this point then, it becomes the concentration of the excess strong base. Any hydroxide from the salt becomes negligible, and so we don't really worry about that anymore. So we go back to having pH equals 14 minus POH of the excess strong base. Okay. So as you do these problems, what you need to figure out is, where on the curve am I? Where am I on the curve am I? All right, so if we look at a bunch of different titration curves for different weak acids along that are being titrated, we can definitely see a difference in things going here. This black line here is the titration curve for a strong acid. Okay, you'll notice the first thing that is for strong acids, our pH is at 7. For anything that it's a weak acid, the neutralization pH gets higher and higher and higher. Okay, so the pH at the equivalence point is above 7. The other thing that you'll notice is that range, this steep part of the curve, is much longer for the strong acid, and it can be much shorter for the weak acids. In fact, The weaker the acid, the shorter that steep part is. Okay. The other thing that happens is at the same concentrations, the solution, of course, has a higher pH if it's a weak acid than it does when it's a strong acid. And that's just simply due to the idea of weak versus strong. We're going to have more hydrogen ion dissociation here, less hydrogen dissociation here, and so as a result of that, you end up with higher starting points, smaller transition periods, and a pH equivalency above 7. Titration curves also help us when we're talking about pKa's and pKb's for different acids and bases. If you look, there's a pattern between the Ka and the pH. Okay, so if I look here, my Ka is 10 to the negative 8. Okay, and if I think about what pKa would be, so if 10 to the negative 8th pKa would be 8. Okay, well, that's right here. Likewise, if I took the pKa of 10 to the negative 6th, I get 6. If I go pKa of 10 to the negative 4th, I get 4. Strong acid, or negative 2, I get a pKa of 2. And so what you will notice for these is that as we go ahead and look at them, the pKa is equal to the pH when you get to the midpoint of the shallow part of the titration curve. Okay, we did this before the other day when we were generating the Henderson-Hasselbalch equation. We saw that pH equals pKa when you are at the ideal conditions for a buffer. That happens at that halfway point of our titration chord. Okay, so if we have an unknown weak base, strong acid, we get the exact same concepts, but a reverse curve. So we start off with a pH that's governed by Kb. We then start adding a strong acid that produces conjugates, but we still have some of the weak base in there. And so as a result, in this region, we have a buffer. Okay, and we can see that again. As we add acid, it does not change the pH range very much. Same thing here on that first part of the curve. When we get to the midpoint, whenever that midpoint is, the pOH at that point in time equals the pKb. We then end up with a steep portion of the curve, and we'll note that halfway down that curve, the equivalence point occurs, and the equivalence point is going to be less than 7. Because we're dealing with a salt situation where we have a cation, like maybe aluminum 3+, that will react with water to form aluminum hydroxide and H+ ions. And so you'll end up with a pH that's a little bit less than 7. And then, of course, at the end, you have excess acid. And so, again, at this point, the pH just becomes the concentration of the excess acid that's involved. All right, so another key question that comes along with doing titrations is what indicator should you use if you're not using a pH meter? Well, lots of different indicators will turn colors at different pH over different pH ranges. And so depending upon what you are doing, what you want to have is you want to have an indicator that changes color at the equivalence point. Okay, that's optimal. However, in practice, that's not really super necessary, because if we think about our titration curve, as long as we have something that changes somewhere on this steep part of the curve, it doesn't really matter, because that portion of the curve is so steep that we can't really see the differences in pH values along that curve. So we know exactly how much of our acid or our base we are adding. So in practice, it's not necessarily to have exactly an indicator that changes color at the equivalence point. You just got to have something that changes somewhere on that steep part of the curve. So as we just said, any indicator that begins and ends color change on the rapid change portion will work. Okay, so for example, if we have a strong acid or a strong base, Oftentimes in general chemistry or in honors chem, we use phenolphthalein because phenolphthalein changes color between a pH of 8 to 10. Well, on a strong acid, strong base curve, that's enough. It will change somewhere on the steep portion and we'll get the right amount of HCl in this particular case. We could also use another indicator, methyl red, that changes color between 4 and 6. Why? Well, again, because it's on the steep part of the curve. So we know that if we need to figure out how much HCl is, anything that starts and ends on that steep part of the curve is one that is an indicator that will work. Right? Now, if you remember, we said that when we have a weak acid, the rapid rise region is smaller. Okay, so we don't want to miss our equivalence point. So in this particular case, we know since it's a weak acid, our equivalence point is going to be above 7. So in this particular case, phenolphthalein is still going to work because on that steep part of the curve, between 8 and 10, we can go ahead and see the color change begin and end for phenolphthalein. Methyl red, however, changes color between 4 and 6, and for our weak acid strong base titration that we had over here, the steep portion of the curve is between 7 and 10, and so again you would completely miss, or that color change would happen well before you got to the equivalence point. Okay. Same idea for a weak base strong acid titration. Here the equivalence point again is below 7, so phenolphthalein is not going to work. However, methyl red will be in that steep part, and it does still work. All right, one small extra piece, and we won't have to actually do any calculations dealing with this, but what we do need to understand is that if I titrate a polyprotic acid, you'll get 3 different equivalence points, one for each hydrogen that gets pulled off. So here's the equivalence point, here's the titration that's pulling hydrogen off of H3PO3. Then you get an equivalence point where you have H2PO3 left, so then the second hydrogen starts getting pulled off. Here's the equivalence point for the second hydrogen coming off, and then this is HPO3, so we actually would still have a third one up here that would get us eventually to just PO3 existing at the end. Okay, so for this particular thing, when you titrate a polyprotic acid with a base, there's an equivalence point at each dissociation. And so you can actually, again, find out the pKa for each of these dissociations by looking at what is the pH at the midpoints. Okay, so it might be something like that. So 10 to the negative second, 10 to the negative 6.5, and up here 10 to the negative, 14 or something like that.